So a bit about myself. My name is Bøgh Fangel. I work at a company called Luna. I've been there for about 4 years. Before that, I've been implementing distributed systems in various companies since 2004. Event sourcing wise, my experience isn't that long. We started doing event sourcing about a bit more than a year ago. Our first event source service went into production around this time last year. So we're pretty new in this space. Okay, a bit about the agenda. First, I'm going to give you a bit of context. What is Luna? I guess most of you don't know what Luna is. A bit of history, the evolution of our tech stack, which is important to understand why we chose event sourcing. Then a bit about what it takes to build a bank from scratch, primarily concerned about our tech vision. And it's this tech vision that has guided us in our implementation. And finally, we'll arrive at event sourcing, why and we chose that, and how we're doing it. A bit about some patterns we've seen emerge from our implementation. And finally, some challenges and learnings if you yourself are going to go this way. So, what is Luna? Outside of the Nordics, there's not very many who know us. We are a smartphone-only challenger bank, founded back in 2015. Meant to, we are trying to disrupt the banking industry. So from the beginning, at the start, the business model was to build on top of an existing bank and then build our experience on top of that, providing our experience using the partner bank, but trying to hide the partner bank as much as possible. From the beginning, it's been in our DNA to deliver a best-in-class user experience and also a best-in-class support of our users. We went live in 2016, and currently we're present in Denmark, Norway, and Sweden. A few facts. Right now we are a bit more than 100 employees, of which 25%, 25, 30, around that number, are developers. We have 150,000 users who together produce more than 1 million. It's probably more like 1.5 million transactions per month. Our platform right now is made up of 100 microservices-ish. We lost count. And we are running 3 Kubernetes clusters on AWS. So that's some facts. Here's a quick view at the evolution of our platform. As so many other startups, we started with a backend in Rails. And a few Java components with integrations to our partners at the time, the beginning. The backend was running on top of Postgres, managed by AWS, and everything was deployed in AWS using static Docker Compose. So I guess a very common setup for a startup that has to do something very quickly. Since then, a lot has happened. We're right now running a microservice platform, as I said. We've broken up the monolith. That adventure started in the summer of 2016. So as you can see up there in the corner, Rails is still there. It really takes time to kill your legacy. But right now, it's the size has it's very much more slimmer than it was before, and it's actually only acting as an adapter into the Danish clearing system. We have a lot of different types of services, sort of grouped in core services and feature services and adapters to various partners delivering part of our product. We're still in Amazon, but now using Kubernetes in a GitOps style, we have a very active DevOps team who's also doing a lot of speaking about this. So we have a lot of talks about that, and we have some open source projects around GitOps, DevOps. There's some links later on. We've added Rabbit as a message broker, so all services communicate using Rabbit. All business domain events are published on Rabbit. We're still using Postgres. That's an example of what Nat talked about earlier. Sticking with some boring technology. That can actually be a very good idea when embarking on something new. Just use some technology that you feel good with. And we do with Postgres. It's well-known technology, and all services are primarily using Postgres. Okay, so a quick assessment of that platform. It has served us well. It has made our growth possible. On the good side, the microservice architecture really delivers on its promise. We get autonomy to our teams. We're running a Spotify-like squad model with autonomous squads, and they can deliver new features fast without wrecking all the other stuff. Furthermore, the standardization we've made across services and the DevOps setup gives us a very maintainable platform. The messaging part is also working very well. It's easy for services to produce events, and it's very easy for consumers to start consuming and implement new features on top of already existing events. On the bad side, messaging again, and that's because we don't have 100% delivery guarantees in the messaging due to some of the choices we've made. So once in a while, that causes some consistency errors, which isn't that good. Furthermore, all of our services, nearly all, are CRUD services, so we're updating state. Once in a while, that causes some headaches when we have to figure out how did this user's data end up in the state, because we have updated it, so we really don't have the history of the state. Okay, so that's a bit of history, which is important to understand what I'm going to talk about now. So let's look a bit to the future. About half a year ago, in August 2019, we received our own banking license. So we're actually going to be our own bank now, a real bank. The reason for trying to get that banking license is pretty simple. It will give us the opportunity of providing a more complete banking experience to our users, but also open up a lot of new revenue streams. We are funded by investors, and at some point we should hopefully be profitable. So getting the banking license is a part of that journey. So the goal for this year is to get our new banking platform up and running, get all the existing users migrated, and offer this complete banking solutions to all the Nordics, Denmark, Sweden, Norway, and later on Finland. Right now we're in a closed beta, about 10-15 employees running on the new bank, myself included. So I've been out in Amsterdam testing my new card, which has been extremely fun. But what does it really mean to be a bank? Well, we're in the middle. To the right we have national clearing, and to the left we have a card processor. So the card processor makes it possible for our users to pay with a card, and the national clearing makes it possible to get money into your account or out of your account. Pretty simple. How hard can it be? Well, of course, it is a lot more complicated than that. And the primary reason for that is that we're dealing with people's money. So when we deal with money, there's a lot of regulation and also a lot of expectations. So ask yourself, what would you expect, or what do you expect from your bank? Well, I certainly expect my bank to be trustworthy. I also expect it to be secure, and I expect it to be correct. When we started this a bit more than a year ago, we knew we were applying for this banking license, so we started slowly thinking about what should our platform be like. So we sat down some developers, and we could all agree on this. But we dug a little deeper into this, and our conclusion was that beneath these words there's something else, or at least we think that there's another property which will enable us to get these characteristics. So that single property ended up as our tech vision, and that property is traceability at all levels. So nothing should happen without us knowing, and our system should never be in a state we cannot explain. That's what we have seen happening in the current platform. So we really want never to be in a situation where we cannot explain what happened. At the end of the talk, I'll come back to how this is actually going to deliver on the other characteristics. But first, let me dive a bit more into this traceability at all levels. So in the era of microservices, Kubernetes, and the likes, traceability has normally, or is normally understood as distributed tracing. Tools like what Open Tracing and Jaeger Zipkin can provide in the observability space. Of course, that's really important, and we also want that. We want to be able to trace across service boundaries and across asynchronous boundaries, have distributed logging which we can manage and search through. But we want our system to provide a bit more. So to us, traceability does not equal distributed tracing. We don't want this traceability to depend on developer diligence, to have the right log statements, provide the right spans for the tracing, etc. We want it to be intrinsic, something which is built into the system by design. So let me take a little detour. This code snippet, with a bit of editing, I've seen this a few times in the code bases I've worked on, and more than once a support case has ended here. Trying to figure out, well, how did that actually happen? I thought it was impossible. How did it happen? Head scratching, searching of logs, trying to figure out what happened. So let me see how many others have been in that situation. Halfish, okay, great. No matter what your answer had been, I have proof that I'm not the only one. Because if you do a search on GitHub for this phrase, this should never happen. Have you tried to do that? I guess not. I have. And the result is more than 500,000 code results on GitHub where we have this should never happen. That's quite fun, I think. But, well, yeah, so that sort of proves to me that I'm not the only one having that learning. And what can you learn from it? Well, my learning is that production is the place where the impossible happens. If you can think of some very unlikely situation that could occur, but well, it's probably not going to happen, at some point in production, it is going to happen. And even worse, impossible things you think are really impossible, they'll also happen at some point. So, this is precisely what we mean by this traceability. What we want is an intrinsic property which can explain cases like this, explain the impossible. No guesswork, no head scratching, no searching through logs, just something built into the system which will tell us this. So that's my definition of traceability. So in the face of errors, we don't want to have to say to our supporters, well, we really don't know what happened. You have to say something like this to our users. That's not a good situation if you're a bank. We want to be able to tell our supporters that, well, we know we have an error here, but you can say this to the users instead. Something happened to your money, but we know exactly where it is, and we're going to fix it. So that's where we want to go. And this leads us, of course, to event sourcing, otherwise I wouldn't stand here. Because we think that by its very definition, event sourcing has some of the properties which will lead us to this. So the very idea built into event sourcing will support this. Often, event sourcing is thought of as just a different way of persisting state. However, there's more to it than that. There's a shift of focus. So you shift the focus from the state to the events. So instead of thinking about what state is this entity in, you think of what has happened historically. And then the state is a byproduct of all those events. And it's this very shift of focus which is exactly what we want in order to achieve inherent traceability. And the main reason we chose event sourcing. We want to shift the focus onto what has happened in the system instead of the actual state of an account or a user. So, we decided on trying out event sourcing and just, well, we've already heard earlier today that event sourcing right now is in a place where we're all trying to figure out what is this, find the right words for things and agree on the terminology of the subject. So just to make sure that we're all on the same page, this slide will be a presentation of what an event-sourced component or an event-sourced service in the Luna setup, what it consists of. Some of you, it'll be pretty basic, but maybe there's also someone in here who actually takes something out of this. So, first of all, the fundamental thing is the event stream. So we store that in some storage. It has an important property. It's an ordered sequence of events representing what has happened in the system. We structure and organize our event streams around the obvious domain entities in the domain. So we could have an event stream for user, one for an account. But also, we're also using event streams to represent the act of doing a transfer or the act of paying some payment slip, something like that. So those streams are very short-lived, whereas users and accounts are long-lived event streams. The next thing is, of course, the protection. And as we just saw, for those of you who were here before, it's just a fold left over the events in the stream. Then we have the concept of an aggregate root. The aggregate root is a well-defined entity in the domain. It's technically made up of an event stream where we store all the events happening to this aggregate root, and a projection to hold the current state of the aggregate root, and then some business logic. The business logic is the write API of the aggregate root, and it protects the integrity of the entity. So it's the only way we can add events to the underlying event stream is through this business logic, the command handlers of the aggregate root. And it's pure functions, just as Jeremy showed before. This piece of code has two inputs, the command and the current state, and it can do no side effects. It can only do one of two things: either fail the command if something is not valid, you don't have money on your account, for example, or it can publish one or more events. Nothing else, no side effects, which makes it very easy to test this logic. But of course we also want to be able to do side effects. So the side effecting things is all in the handlers, the event handlers. So a handler will get an event from the event stream when a new event is added, and this is then where we can do side effecting behavior. So the side effects could be calling some external system, publishing a message, or looping into the system itself and executing a command on a different aggregate. So that's basically what our event source services are made up of. So what about the implementation? Yes, I probably didn't say it, but we've ended up being primarily a Go shop. We started our microservices in TypeScript with Node, but now everything new is written in Go. In Goland, we did a sort of looked around for event sourcing libraries in Go. There's a few, but none of them are maintained by more than one or two developers. So we actually ended up writing our own library. Actually, we did it twice because the first version wasn't really what we wanted it to be, so we did it over again. We are planning on open sourcing that. It's not completely ready for the rest of the world yet, but hopefully later this year we'll open source it. We chose another choice of boring technology, just stick with Postgres. So we're just using Postgres as a JSON storage. The content of the events is just a JSON blob, and then there's the sequence number and a timestamp and ID of the event. That's everything we need. Then we're using in-memory views for the aggregate roots, and SQL back views will come later, hopefully this month. So this is very, very new. All I'm going to say for the rest of the talk is just out of development. So in 2 months we have maybe changed to something different. And now, just to be able to actually show some code, I had hoped that we had already open sourced Apogee at this point. Well, didn't happen, so the only way I can show you some code is on slides. So this is taken from an example which is in the library itself. The top part here is it's a to-do list example, a very simple example where we have a to-do list and we can add items to it, and we can check items and archive items. So a bit more complicated than the light bulb, but not much. So the top part is the state, defining the current state of the aggregate root. It only has two properties, a timestamp when it was created, and then a map of the items and the item state. It only contains just enough to be able to determine the action. When we get a command, we should be able to determine is this a valid action or not. Then here's an example of an event, just a struct. So an item has been checked. It happened at some time, and then an ID of the item. And down here we have the application of an event to the state. So that's simply looking up the item in the map of items, check it, and put it back. Yeah, in Go, if you don't know, Go is not good at immutable things. So you have to get used to that. This is mutable. So it's not like in F# as we saw before. That's what we really like to do, but you have to code around it in Go. And here's then a command handler. So all the command handlers are defined as methods on the state. So we get the parameters is the command, and we have the current state. So the Apogee library will take care of loading the state when you call this. So you get the state at this point in time, and the sequence number that the state corresponds to is then also encoded in the unit of work up there. So the unit of work functions as the transaction in the event sourcing system. So we do some checks. If it's an empty item ID, we fail. Look up the item in the current list of items. If we can't find it, well, then we also fail with a specific failure code. If the state is already checked, well, nothing to do, just return. Else, we publish a new event. Very much like what we saw in the talk before. Yeah, so that gives you an impression of what this our library is, and hopefully later this year you can actually use it if anyone is interested. So that was the code I was going to show today. Okay, so in order to make an event-sourced application work, we need one crucial property: guaranteed event handling. The handlers are crucial. That's where we have the side effects, the thing that makes the application tick. So we need to be able to ensure that all handlers will get all events in the proper order and with as low latency as possible. So how can we implement that? Well, first we thought, well, we can probably do that inside the library. So it's something like keeping track of how far have your event streams come and how far have your handlers come, and then just making sure that you always get all the events to the handlers. That would give us more complexity in the library, so we tried to look around for different ways of doing that. You could do a more generic outbox pattern where the events are put in an outbox and something else is taking care of publishing that, and an inbox on the other side taking care of that the events will actually be propagated to the handlers. But we'd really like to find a piece of technology we can just more or less pull down from the shelf and then use that. So last month we did a proof of concept using Debezium with Kafka. So if you don't know what Debezium is, it's a CDC, change data capture tool, which will contain the database and publish all changes to a table on Kafka. So right now, this is how we think we're going to do this and guaranteed event handling. The table is very simple, and since we're only appending, the only type of change there'll be there is an insert of a new event. So the model is really, really simple. So we just have to subscribe to the Kafka topics and make sure that the handlers will then get these events. There's a thing about the order, but you can control the partition key based on what's in the table. And inside the same consumer group, you get the proper ordering. So that's how we think we're going to do that. Okay, so that actually leads to the patterns. Patterns we've seen come out of our implementation. It has been very much a trial and error process. We've been implementing various parts of the new banking platform, and then these patterns have emerged. So the first pattern concerns public APIs. So if you think back to the very, very simple drawing of what a bank is, we had us in the middle and national clearing to the right. So this is that part of the drawing. In reality, we have the banking core, and then there's an adapter. Because this API up here to the national clearing, that's typically some old piece of technology over here. In Denmark, there's a bank central here sitting on a mainframe where they have put a REST API on top, or REST. It's REST with a lot of weird behavior coming from the actual mainframe. So it's a synchronous API. So the model in our new banking core is that for each of the different national clearing systems, we'll have an adapter. And this adapter will then communicate with the bank core asynchronously. And in fact, the banking core will know nothing about this part. So the adapter is the one executing stuff and also receiving stuff from the clearing if money goes into the account. So this part, how can we expose a public API between the banking core and the adapter? On the inside in the banking core, we have the internal event stream. It has some really nice properties, an ordered sequence of events. So we'd really like to have that property on the outside as well. But, of course, we shouldn't expose the internal event stream. That's our internal state. So, who was it? Yeah, one of the other talks, it was stressed. Never expose the internal event stream. It's your dirty underwear, right? So the way we are solving that is by producing an external event stream based on the internal event stream. So it's essentially a handler writing to an event stream. And we can keep track of the source events on the inside in order to guarantee this traceability, that an external event that we publish somewhere, we can trace that back to what internal event led to this external event. So here's a small drawing. So we have the internal event stream, a handler, maybe a projection if we need to keep track of some state in order to be able to publish the external event stream. And on the right, here we have two event streams on the outside. We have the possibility of exposing several derived event streams. This one has fewer events than on the inside, so it's a more focused event stream. And the top one has more events. There's in this case, there could be a requirement that you have to invent another type of event based on one of those. We actually have that when you withdraw or do something on the account. We'd like to actually publish a balance changed event. That's not in here. In here we only have transactions on the account, but on the outside we'd like to have a balance changed event for someone else to listen to. Now the balance was changed on the account, so this handler will just invent a new event based on the internal event stream. So it also gives a way to do versioning of your public APIs. You can just add a new one, and consumers can then switch over to the new external event stream, and at some point you can then deprecate the old version. So this pattern of using external event streams for all the communication, that's how the banking core and the adapters are communicating in both ways. So the adapter listens on the banking core, and the banking core listens to the adapter. That's how we do this communication asynchronously between the parts. So the next pattern is distributed flows, or distributed transactions, or sagas. We represent that as aggregate routes. Actually, the aggregate routes here are used to represent a state machine, where the state represents how far we have come in this process of doing some distributed flow. The state of the aggregate route determines which action handlers should take, and of course all side effects are in the handlers. And as I said, we're using the public event streams as API. So here's a quite elaborate example. And this is actually how we have implemented transfers. So here on the left we have the bank core, and on the right the adapter, in this case the Danish adapter. Inside the bank core we have the account, long-lived aggregate route, and up here there's a transfer aggregate route representing the act of doing this transfer. Likewise, in the adapter there's a transfer aggregate route representing its side of this distributed flow. So a request comes in from the user, which will be validated on the account, and let's say it's valid. That will then publish 2 events on the account aggregate route: transfer initiated and funds reserved. So we do a reservation of the money you want to pull out of the account, so you cannot use that money for anything else from that point on. Up here we then have that handler, which will get this event and cause an action on a command on the transfer aggregate to initiate this transfer. So now we get an initiated event on the transfer aggregate inside the bank, core. And another handler will grab this event, publish an external event on the external event stream. It's not included here in order not to clutter, but in between here there's 2 external event streams, one from the banking core and one from the adapter. So after step 3 we don't get any more events on the inside, but we have an event on the outside. Then in the adapter, a consumer will get this event, cause a command on the transfer aggregate inside the adapter. Now we have this initiated. A handler will get this event based on the state of the transfer aggregate. It will do whatever it must do in that case, which is of course try to do this transfer in the clearing. So let's say that times out. So the request timed out. We really don't know what we should do, but we store that results in an event timed out on the transfer aggregate. That event will then reach the handler again, and the behavior when the state is timed out is, of course, to retry. So it'll retry the action again, and let's say it succeeds this time, then a succeeded event is added to the event stream. And now we have to go all the way back, right? So a handler here publishes a succeeded event on the outside. The consumer in the banking core consumes that event, causing a succeeded event on the transfer aggregate inside the banking core. And finally, this handler will then handle that event and execute the transfer completed command on the account aggregate. This will then give rise to a transfer completed. Then we'll remove the reservation because now the money shouldn't be reserved anymore, but instead there's a transaction created event. And this will then propagate up to, outside of the picture here, we have a transfer service actually handling the request from the app. So it'll get that event and the action is then completed in the app. Yeah, this slide is only there for completeness afterwards. We have all the numbers and all the events. Okay, so some key takeaways. Again, guaranteed event handling is extremely important. If that fails, then the process stops. So down the line, we have to have some metrics on that to be alerted if something goes wrong. It's extremely important for us to get that done. But we get maximum traceability. All that goes on as part of that transfer is recorded as events in the various aggregates taking part of the flow. And of course, errors are going to happen at some point, remember, production. But we can see those errors directly in the aggregates. Which leads me to the last thing I'm going to talk about, our implementation, error handling. Failures are first-class domain citizens. Failures are not exceptional. We strive to narrow down the part of errors which should be treated exceptionally. Just as in some languages where errors is just another value, it's just another type, it's not anything exceptional. For example, in Go, there are no exceptions. You just have an error as a value. So we try to treat as much as possible failures as just part of the domain. It's something you should expect happen. So your domain should also treat those errors that you expect to happen as first-class citizens. Furthermore, idempotency is crucial, both in our own internal APIs. The transfer service that was over here has to be able to retry the request towards the banking core. If we have a timeout inside our own platform, well, the only thing it can do is try to do it again. And rest assured that if it actually went well, then, well, you'll just return the same result and not do the transfer again. But we're also depending very much on the external API from the clearing, that's idempotent. If we don't have that, then we are really on thin ice when we get timeouts or crashes. We have no way of knowing, did it actually occur, this transfer, or not? So fortunately, the clearing system guarantees that for us. If we didn't have that, we would have to figure out how to, after a crash, after a timeout, have some read endpoint where we can read, did this actually succeed or not, and then take action based on that. Okay, so let me go back a bit to the tech vision and revisit this. What about the other properties? Correctness and consistency. Correctness. I hope you'll agree with me that 100% correctness is impossible. So, what can we do? We can do our best, test our software as much as possible, but even though we test, we'll make mistakes. So, what we think is that, well, if you can understand your errors, then you can also fix them. If you don't understand what has been going on, then the chance of correcting it is a lot less. So that's how we think that this inherent traceability will enable us to eventually get to a correct system, one error at a time. So if we can understand the errors when they happen, we can fix them in the system, fix the data, do whatever is needed in order to fix it, go back to our code, make a test, and fix the code. So that's what we mean by traceability leading us to correctness. And furthermore, in event sourcing, error correction is not different from what you do all the time. The only way you can fix an error in event sourcing is by putting another event on the event stream. So compared to the CRUD services, where fixing something in the state is doing an update, we can always go back in event sourcing. If the correcting event you put in the stream turned out to be not completely correct, well, you can just add another one, which isn't the case in a CRUD service. You might not be able to go the other way after you've done the update. And consistency. Well, this is where the ordering of the event streams is important. We think that by exposing external event streams which have the same properties as on the inside, an ordered sequence of events, that actually empowers the consumers because now they can reason about the events they receive. If they receive, a consumer receives event number 10 and the last one is always number 8, then something is missing. If that occurs, well, we could actually also empower it to be able to retrieve the old events. If we put an API on top of the producer or somewhere else where we have the events lying, we could put an API on top of that and enable the consumers to actually retrieve whatever events it hasn't seen yet. Of course, the only thing we can guarantee is eventual consistency. But that certainly is a lot better than what we have in the old platform, which is maybe consistent. And in the old platform, the consumers have no means of reasoning about the messages they receive because we don't have this ordering of events. Okay, so I'm nearing the end of the talk. What's left is some of the challenges and learnings we've had during our implementation. First, and not very surprisingly, event sourcing is a perfect fit with the DDD. Together with the event sourcing part, we also started doing DDD in a more formalized way, and the things fit nicely together. But it's a different mindset. When coming from services which are CRUD services, you really have to wrap your head around this way of thinking. We didn't do DDD in the CRUD world in a formalized way. We thought about the domains made up by the microservices, but it wasn't really formalized. In the implementation of the banking core, we've tried to actually also adapt some of the practices from DDD. It can also, especially in the beginning, when you start doing this, cause some mental overflow, where you have to implement a certain thing, but you have really no idea how to do that. And you have to do a lot of searching and figuring out how to actually implement this using this tool set you have available. So you certainly have to leave room for experiments and failures. That's how we learn. Try things out, fail, and try again. Furthermore, we, at least up until now, we really think that event sourcing delivers on this promise of traceability. We went live with this closed beta about a month ago. So since then, we have actually been using the system for real, and it's such a relief to be able to look at the event stream and see, oh, that happened, oh, here's what went wrong. But, and there's a but on all the slides here, it's not necessarily mainstream tech, depending on your tech stack. In our case, in Goland, it certainly isn't mainstream. In the .NET world, it's a lot better. And the part about guaranteed event handling, that's a challenge. You have to figure out how to achieve that. Finally, we've also learned that there's a tremendous power in these immutable event streams combined with CQRS. But immutable data can also be a challenge in itself. What about GDPR? Fortunately, we're in the financial space, so we're actually allowed to keep a lot more data for longer periods of time than anyone else, which is nice. But we eventually have to figure out how to handle that. And if your event streams are immutable, at some point we have to look at migrations, migrating event streams, and that could be also an idea of dealing with GDPR. We have already done this, compensating events. That's the only way you can do corrections if something went wrong. So you have to implement some tools or handles to be able to do correcting events on top of your event streams. Yeah, and with that, I'm actually done. So here's a few links to our tech site. We have a blog where we try to write about what we do, and a collection of talks. I have some colleagues in the DevOps team that are really active in the community. They've been out speaking at KubeCon and other conferences. And we have some open source tools, DevOps focused right now, but that's also where Apogee will eventually have its own life. So take a look at it. My slides will be up there, if not later today, then at least tomorrow.